Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're really pleased to have Eva Tardosh here. If you would go back one, and I could know what you're talking about.
I'm sorry, I didn't mean to do that.
She's visiting from Cornell for 2 days, and she's going to be talking about pricing games in networks.
Thank you. So thank you. It's nice, always nice to be here. I gather I made the tactical mistake to show up instead of Vine. Which maybe was a mistake on its own, but also some people are gone at Vine who probably would have been also nice to talk to. I apologize. I first made the decision not to go to Vine and then didn't actually pay any attention when Vine was. So, sorry. So I guess I will actually be talking about a very concrete game, but under Jennifer's suggestion, should start with a little bit of introduction to the area. So I guess when I mean by network game, I sort of mean a network as maybe the internet as my favorite network, for example, but maybe there are other examples too. There are tons of things that in the internet are done or provided by multiple independent parties that we better model as games because different companies, such as the ISPs, are obviously pursuing their own selfish interest. But I guess there are other things that people sort of model as networks, as independent interest. The browsers, even though maybe are provided by some companies such as Microsoft, they supposedly, or maybe not even supposedly, are pursuing they designed so as to pursue the interest of the user of the browser. The routers, though almost all of them are provided by same one company, Cisco. They're all supposed to also still provide someone's selfish interest. They're designed to cater to the owner's interest. Servers, I guess, care about the particular service. If you provide a web service for people to read New York Times, then I guess your interest is to provide as good a service for the New York Times readers and not care about the other guys. So there's a lot of things, even if they are actually owned by a single company or provided by a single company, that naturally have to cater to the selfish interest of some set of users. And this is what I want to model here. This has been a flourishing area over the last number of years. There's a lot of interesting papers or a lot of interesting directions. And let's just, here are some of my favorites. And I'm sure there are many others, and maybe some of you disagree of which one would have chosen a different set as your favorites. One thing that my set of favorites had in common, that they used a sort of complex network. They allowed you to think about graphs and networks and arbitrary networks, and they were sort of complex that way, but they were rather simplistic, all of them. In the other aspect, they used very simplistic objective functions. So I guess there's the delay and routing and load balancing games where you can think of arbitrary complex networks in which you're routing, but you should say that your objective function is a very simple one, delay, which is an easy one to use, or load balancing, the same thing, which they usually response time, which is another name for the very same thing. And there's these other guys, which somehow were the other category, where, again, the objective function is cost, which I guess is in principle a more complex objective function. But in practice, and I'll show that maybe in the next slide, again, the way the cost got molded in these particular games was very, very simplistic. So this is on a class of games where the surrounding or the network or the environment was as complex as it could get, arbitrary graphs, but on the other side, the way you model people's objective functions either via delay, which is anyway simplistic, or via a very simple way of modeling cost, that the objectives were very, very simplistic. This gave us give us a proof technique, the potential function proof technique, which is very, very powerful and could do a lot of things, especially in this category of games, where objective functions are very simplistic. And I guess looking at the audience, maybe you all know what it is. I only have like 2 slides to remind whoever might not know that the potential function is a kind of function, maybe used also in online algorithms and many other settings, where magically there's a single function phi, so that when someone selfishly changes move, then the phi, this potential function somehow goes down. You might be, up front you would think these things don't exist, and I guess the line is they almost don't. They rarely do. They exist in one class of games called congestion games. Congestion games are, and here's one picture from that I use for a network design kind of game, where somehow the only thing that cost or delay or your objective functional event depends on is this one parameter named congestion, how many other people you share something with. So this is about as complex as a congestion game gets. In the game that's supposed to be indicated there, the users are colors. They choose edges in a graph. They have some sort of rules for them. In that game, they want to connect the nodes. And the cost depends on every edge and depends on how many other people share the edge. That's what congestion game is. And what the theorem here says is that something has this magic potential function if and only if it's a congestion game. So you can read this as the first version of reading this theorem was, that this is really cool. Congestion games model an awful lot of things, and they are potential games. And if you read it this way, oops, I guess this is the typical congestion function. I'm going to, then you can read these nice consequences off of this. Potential functions exist. This is beautiful. Why is it beautiful? For example, we know that pure Nash equilibria exist. You can minimize the potential function, and that's a Nash equilibrium. Even better, you can view that you let the pair go and best respond automatically, then they're going to reach an Nash equilibrium. Why? Because they're minimizing this function phi. Sooner or later, they get to the minimum, and then they're stuck. And maybe next step up, you can even evaluate the quality of the solution. If it happens to be the case that the potential function and your real cost are not completely unrelated, then they're related by an inequality like that, you would say, okay, these guys are minimizing phi. They're a little bit wrong. They should have minimized cost, but they're doing a little bit wrong thing. They get a little bit wrong answer. And that gives you results on how good the price of energy is. There are 2 classes of games that I have looked at or people have looked at. Yeah. Can I go backwards? Here it is. 2 classes of congestion games that people have looked at very generally, and for a while, I guess my feeling was that, gee, this is a very rich class of games, and in some way it is. It can both more sort of delay-style games. So these are congestion games, which, as like routing was one of them, the delay guy here, is when you think that the cost is increasing with congestion. People would like to avoid congestion. This is like routing your car on a highway. You don't want to go on routes with a lot of cars. Or you can use what we call cost-sharing games. This is a place where you think of your prime model of cost is the economy of scale. If there are many of you together, it's a little bit cheaper per person. That this cost decreases with congestion. These are coordination. These are sort of spreading out games. You want to be as spread out as possible. These are coordination games. You want to be together as much as possible. And both classes are modeled by these congestion games, and that's kind of neat. That says it's a broad class of games. No, well, it's still a potential game, even if it doesn't have to be uniform on every edge.
No, but he's asking, does it have to be monotone?
No, it doesn't have to be. In fact,
I mean, does it have the same monotonicity?
So you still have a potential game if it's on one edge positive and the other negative.
Yeah, and in fact, I have a potential game even if it's not monotone in any direction. It sometimes goes up and other times it goes down. So you kept the potential game is anything where your cost is solely a function of congestion. So what way would your cost not be a function of congestion? I guess my whole talk after this will start about, well, wait a minute, congestion games are incredibly limiting. So this means that on this edge, your cost is solely a function of how many people showed up here, not who showed up. This is a reasonable model when you drive cars because you really are caring about traffic. You don't that much care whether who actually sits in the other car. It's not a very good model of virtually anything else in the universe. You didn't care about the humans there? Wait a minute, why not? If you think about cost sharing, Cost sharing turned into one of these games because they said we not need to do fair cost sharing. We're going to share the cost evenly. And that indeed sounds fair, and that's turned it into a congestion game. Now I care about how many other people were there so we could evenly share the cost. But even cost sharing is probably as far from fair as it probably can get. If I use a link for my email and so does Microsoft, I should pay half the cost? Really? That's what congestion games do. You should only care about how many other people use the link, not who they are, whether they're big users or small users. I can have all kinds of other complications, but maybe the biggest one is usually coming in with this inequality. In a longer version of this, which would be a talk fully on congestion games, and I guess many of you, I gave sort of this kind of talks both at Microsoft and here, but different talks. But in any event, quite surprisingly, luckily, there are inequalities like this sometimes true. Okay, so if you think of congestion game as a rating game, it's surprisingly, with many, many delay functions, you get a pretty good estimate here with that A function. A actually is surprisingly good. If you use it for a cost-sharing game, again, you get something, surprisingly, it's pretty good. You should be surprised because this phi was some sort of crazy function that happened to have the property that it reacts to users' responses. Actually, it's still written there what it is. It's not the real cost. If you go back thinking of what the real cost is, so what is this phi function? It's add up the cost of an edge, costing, if there are xe users on edge E, then I pretend that there is 1 user, 2 user, all the way up to xe users, and add up the cost with 1 user, 2 user, xe users, and that's my potential function. The real cost, in contrast, should have been xe times c xe, all of them paying this last cost. This is the real cost. Okay, so there's some sort of, it relates to it, it's not quite it. Sometimes the relation, sometimes not. If I assume some monotonicity of the costs, then there's a natural relation. If I lost the monotonicity, which is what Christian suggested I should do, it's still a potential game, so you cash in on the first 2 points, but you probably lose this one, if it's a crazy function.
Don't I need Lipschitz bound rather than an absolute bound? If you say I'm just a little bit away from the minimum, that will not tell you anything. Don't you need
I need something like that too. I need many other things that I'm hiding here. I also need the fact that, so I said that these users are minimizing the wrong function, the little bit wrong function, they're getting it a little bit wrong. Well, sort of. They also use a little bit wrong method to minimize their function. They're using a local search by each of them stepping one at a time. So what they get to the local minimum, not to real minimum. So I also need that the local minimum are pretty good. I need a lot of things for this to work. Kamal had a question which I let him ask. You had your hands up.
You're not allowed to see who's inside the car, but you're allowed to see how big the car is.
No, I'm not allowed to see. And that would be weighted congestion game, and I lose a lot of this stuff, including the potential function. Potential functions only exact congestion games.
You could split the cars in pieces, but then you would have to take into account
I could, but
and that's probably again
well, a bigger problem that I should take into account that your car cannot split between 2 highways. I could think of your car because it's big as 2 cars, but there is a version of this game that insists that your 2 halves of your car drive on the same highway. So it's weighted congestion game, and weighted congestion games are no longer potential games, only the unweighted one. So, okay, I want to attack actually, so potential games I think are beautiful. There are many nice questions one can ask about them, and there certainly are covering interesting classes of games. And looking at the audience here, someone like Anna has not had to be taught by me that not to work on potential games. She wasn't. So there are certainly large chunks of the community who wasn't working on potential games. I have spent a lot of my recent past years on potential games, and I have to admit that one needs to get away from them. And one way to get away from them is the way, is the way, I'm sorry, this forwarder is not working as well as I could, is to admit that life is not full with potential games and a lot of other things. The way I want to get away from them is to keep the network feature, but put in the number 1 feature that everyone else does, for example, like Anna, who's not working, or when she's not working on network sync, is pricing. If you think of something that gets modeled in selfish behavior is offering prices to customers. That's sort of the number one, easiest, most natural thing that economists would tell you is sort of the basic economic incentive kind of thing. You get customers and you offer a price. And if you look at a lot of the pricing literature, that goes to the other direction from the congestion game literature, in that the scenarios are simplistic. They say, okay, one good, very simple, no distinction, everyone wants the same thing, but now you have to offer a price. So what I would like to do is keep my network, but think about pricing as part of the attribute here. And for example, even though money was one of the things in the cost-sharing games, pricing was not. There was no price negotiation as to how to share the cost. We agreed on this even sharing, which sounded nice, but maybe pricing is a better match to reality than even sharing. So I guess my favorite example to what I'm going to talk about, the pricing game in networks, is this map from Europe around, I don't quite know when, 800 or around 1000. That's supposed to be the commercial routes of Europe. I copied it out of a textbook. I don't know how much it matches reality. But there were routes like this that people used to send goods around the world, in particular around Europe, as a trading network. And I guess you want to wonder about two questions. One I really would love to wonder about, but I don't have a lot to offer right now. And one that the talk will be about. The one that I would love to understand is what exactly formed this network. How do you think about what formed this network? And there obviously are two competing forces that form this network. If you are from Europe, then some places, or maybe even if you're not, then you well know that some places there are no routes here. There's some very obvious reason. There's a really high mountain there. They couldn't climb across. So there are some physical limitations that some things are really expensive. But there are interesting ways these patterns evolved of where it's dense and where it's not dense, and that probably had to do with trade opportunities and not with mountains. So there are two forces here. Some places are expensive to put in a route, and some places very desirable or not so desirable to put in a route, and some very combination of two outcame a network. And I think it's fascinating to how networks form this way. At the moment, I guess as a step number one of this process, I want to understand, suppose you have a network, what exactly happens on this network? How does trade get modeled? If you think that I'm talking about the 800 or Europe around 1000, and hence it's not really limited today, I think trading on a network models an awful lot of things. So to formulate this in sort of a maybe simplest game theory that actually there's a lot of beautiful literature about, is a version of this with no explicit modeling of traders. It's a buyer-seller network, so there are these sellers which have these green tokens which you see on them, and then there are buyers who would like to have the green tokens. And I guess in red I indicated a matching on which you maybe can send the green tokens up to the buyers. And in fact, I indicated what I'm going to think of as an optimal matching, namely it ended up sending the tokens to the people who won them most. They had valuations written on the edges. This is a matching problem that has been studied both in the econ literature and obviously in the CS literature in sort of trying to understand matching markets. So if you want to be a bit more fancy, and I guess in the paper we want to be fancy, in the talk I won't want to be fancy, you can of course assume that these green tokens are not completely identical and that the buyers distinguish the green tokens, and some wants one and the other ones wants the other. They can have different valuation for the green tokens. And if we want to be even more fancy, which again in the paper I want to, but in the talk I won't want to, I think I should assume that the sellers distinguish the buyers. I don't know what the tokens are, but the prime example of what matching markets, I think the best application of matching markets, or more fascinating application of matching markets is job matching. In a job matching, the green tokens are the humans, and the circles up there are the jobs. And on that case, of course, as an employer, you would want a good employee, but as an employee, you want a good job. And so there are valuations on both sides of this market. You value some things more than you value other things. I want to have you keep this kind of situation in mind, but for the simplicity of my slides, they all will have green tokens, and I'm going to, for the slides purposes, assume green tokens are indistinguishable, and everyone just wants a green token. It doesn't matter to him which one. But I'm going to, so if you go back to either mostly the econ theory that thought about this sort of matching markets, one thing that they're missing is the slide I wrote in the middle but didn't actually indicate anything in the middle, called the traders. But usually the econ papers offer, and there are many econ theories, and I'll have references in 2 slides from now, is some sort of prices in which say that somehow you're going to, if you look at CS papers, they tend to not worry about how this happens. And they tend to just say, okay, this is a matching problem. You're going to have to match the lower guys to the upper guys. It's a maximum matching problem. You can solve it. Or if you're more into real life, you would think about the online scenario where people show up one at a time or something like that. You don't worry about the economics. If in contrast you look at the economic world, then they usually think about the pricing, and they're going to have the papers usually end up with some sort of offering prices of, how about the prices here and who should make how much money. And they have all kinds of offers for where the prices would come from. Fascinatingly, they don't seem to offer a sort of action-based game-theoretic offer for prices, but instead they model prices in equilibrium prices, or they offer this sort of vague sentence up there, market sets prices. How? How did the market do that? So then you can look at papers like the algorithms papers, like I guess Devon or Kistos, and I'm not sure I'm good at listing all the co-authors, that going to offer efficient algorithm to compute these prices. This is really a computer science paper. There is no way either of these or any of the errant papers. They're not suggesting that that's how markets work. They say, I, in a computer, can compute these prices. Here is how I would do this. Then there are papers like, for example, for a recent one, Richard Cole and Lisa Fleischer, who say, no, what we need to study is the Tatonman process. There's large literature of the Tatonman process. The Tatonman process is meant to be a model of how market works. If there is excess, if you're good in sold, you need to lower your price. If you sold it real early and there's a lot of time left and people are coming, then I guess you should have had a higher price. And supposedly in a process in which you lower and higher prices according to this basic, very simple principle, it should converge, which it may or may not. And if you listen to Lisa and Richard, then what you learn is that if you make very, very restrictive conditions and very specific convergence rule, then it might converge. Usually it does not. So maybe the market works this way, but their theory doesn't actually convince you of this. I'm not sure my theory will convince you, but what I would like to have is a game. This is still not a game. It's possibly a process which may or may not model how markets work. What I would like to have is a selfish incentive, a game theory offering a sort of selfish incentive by a human. And to do that, I'm going to offer you a third class of humans other than sellers and buyers who will somehow be the price setters. So there will be some humans on the market who set the prices. I guess I'm going to skip over this, but there are a bunch of this was a better slide with references, and I can go back to it. So here is what my game will look like. So instead of looking at this very complicated Europe map, I give you a schematic map I just made up. In the schematic map, there you see, maybe you don't because the slide's not so great. There's a river here in the middle. There are 2 buyers and 2 sellers. Okay, maybe more, 1, 2, 3. 3 buyers and 3 sellers. And there are 2 people who decided that, well, like they're going to try to mediate trade. They located themselves around the river. Maybe they own a little boat, and they try to mediate trade over there. And what we're going to suggest is going to, oops, I'm not sure. So here is what the game's going to look like. But I will, for now, assume that buyers and sellers can talk to each other. They're like sort of, they sit at home, they grow stuff, or they sit at home and would like to buy stuff, and trade is mediated by these guys named traders. This is actually a pretty good model of both the around the century turn Europe, and actually a lot of developing world today. So when I gave this talk in a more econ audience, a whole bunch of more developing world interested economists said, yes, actually in Africa, this is how it works. There are people who live off of trade. They travel around, and that's what they do. So this is trade occurs through these intermediaries named brokers, and the brokers will set prices. This broker can tell this guy that, I would want to buy your good for $5, and this other trader can say, well, actually, I'll give you $6. They possibly compete each other to some good number here, so this guy actually makes some money. Same version here. Anyone who could be served by multiple brokers hopefully will get a decent price because he'll buy from whoever offers the better price. This is not only, so traders are offered by different buyers and sellers. The traders will make price offers to sell and buy. Offer prices, they may differ. They may price discriminate. Again, this is a reasonable assumption in trading in developing countries. What you offer in one village can be very well different what you offered in the other village. Sellers and buyers, I will assume, will act greedily. They they choose the best price offered. And then trade will occur. If I have this as a model, this is a very simple game theoretic model. It's a two-step game in which step number 1, all the traders offer prices. Step number 2, the sellers and buyers react to those prices. The traders got some stuff. They hopefully conducted trade. If they did well, they make money. To offer you, monopoly. So I'll offer you 2 little examples to comprehend what's going on. I think it's better than the formal definition. Version 1 is monopoly on one side. So this trader is told monopoly. He's the only trader. They can only trade through him. I assume a full information model. The trader figured out what is the max that he can charge and still make money. And indeed, he's going to make $8 here because he'll take this 1 unit and trade it over. On the other side, you sell a model which is a complete example of what competition ought to be like. There are 2 traders. They're totally interchangeable. They connect to the same pair of buyers, and they're going to compete each other out of business. What does it mean to compete each other out of business? I can't actually tell you. There are many equilibria here, but they all share a property that traders can make money because they compete each other out of business. For any number x, there's one potential equilibrium here in which they offer the selling and buying price x on all customers, and there's nothing much the other guy can do. Okay, so they sort of competed each other out of business. If I go back to my silly example across the river, that of course is a combination of the monopoly. I put together a network consisting of monopoly and the competition. I guess this is on this link, this particular trader has a monopoly, but in the middle he's competing. And in a way, every network sort of looks like this, but not every network is combined of perfect competition and perfect monopoly. So I guess that's one version of the trade. Here's another example that I guess I sort of got first convinced that there's something interesting going on here. That's an example of a single auction. So here is one way of modeling an auction. We have a bunch of traders, each represent a buyer. So this is your personal trader that trades for you. And there's one seller who owns one thing. Now what will happen here? Step number 1, well, in our model, these traders have perfect monopoly over their buyers. So given the perfect monopoly, they offer a really bad price to them. But now they're competing for that one good. So what should happen on the one good they're competing? So I claim that, well, for some, the right thing will happen, and the good will have to go to the person who values the good most. So let's point out that the guy who values the good most values at value 8. His trader can compete the price all the way up to 8. He has the most power. So there's some reasonableness that should happen. But of course, he won't have to compete the price all the way up to 8. It's enough to compete it up to 6. Because at that point, no one can compete him out of business anymore. 6 is the next best price. So interestingly, what had happened is we're going to have a transaction that happens at the second best price. This is the Vickery action, or second price action, except somehow, and a trader makes profit, it makes exactly the profit between the best price and the second best price.
But the buyer on the left at the top doesn't have complete information? Because that buyer can offer only 6, knowing that all the other buyers...
Well, the buyer would. It's a good point. So there are certain in this version where I have every trader attached to a buyer and they're sort of in a pair. In a way, in a real life version, that trader-buyer pair, it's easier to think of them as a couple, or they together somehow. In this business, it's not clear who should make the $2. The way I set up the game, I made the traders move first. So the two of them are in a sharing a dollar game, in which the game theoretic predicted outcome is that the one who moves first gets the whole outcome, and that's what I'm modeling here. If I want to think of the reality of this for real life, and we have a couple of applications of this form where buyers or sellers have their personal traders, I don't actually think that offers a very good prediction of between the two of them who will make the money. In the game theoretic version, it's very, very clear the guy who moves first makes all the money, but that possibly is the wrong game theoretic model. Okay, but I agree that in modeling reality, there is some weakness in there.
But isn't that, I mean, it has to do with sort of the marriage problem and as a desire and not, right?
It has to do with the ultimatum problem. If I actually just take this whole thing away, even the monopoly had to do with the ultimatum problem. So the ultimatum game is that there is $1 on the table, Jennifer and I have to split it. And the system of splitting is that I tell Jennifer how much money she should take and the rest is all mine. And Jennifer either says yes, in which she gets it, and otherwise, or she says no, and neither of gets it. That's the ultimatum game. The game theoretic prediction that I should keep 99 cents and offer 1 cent to Jennifer, which she needs to accept because 1 cent is better than nonsense, which is her only alternative. In reality, people in ultimatum games don't behave this way. But the game theoretic prediction, even if it's not a repeated game, in game theoretic prediction is wrong for human.
Life is a repeated game. We've probably evolved to have instincts for a repeated game, which is why I would take the
Maybe, but even if it set it up not with Jennifer, with someone I never met and will never meet again, people don't accept the 1 cent. And actually, people don't only offer 1 cent, both sides. People don't offer the 1 cent and don't.
It was $100 million. It was $1 million and 99 million.
No, also not.
What do you mean? People will not.
Apparently not. So they tried it. The best I can tell you is that they tried this experiment with $100 and very poor countries. So in very poor places, $100 is a lot of money. That's still not what's happening. And they tried it with people who are only one of the participants is an experiment, is an actual player. That is, the person who takes the money was a fake. Or the person who makes the offer is a fake, and they offer you they said, okay, here's $100, I take 99, do you want the $1? In a place where $1 is real money, and people say no.
There's a heavy reputation cost of accepting the
Yeah, but you're not supposed to. Okay, this is a very nice discussion, and actually I have been involved in work that's trying to attack that question. For the moment, I just accepted the game theory prediction, even though it's wrong. Oh, sorry. I'll tell you in a minute where this comes in, and I guess I'm happy to either afterwards or even maybe as part of discussion tell you about some other thing we're trying to do with some of the same set of authors to try to attack this. And this work will turn out its own relates to cooperative game theory and will relate to marginal cost, but I'm using a very simple traditional game theoretic approach, which is subgame perfect equilibrium. I let the first guy move first and the second guys have to react. The prediction of subgame perfect equilibrium in the ultimatum game is Jennifer has to take the penny, and I know that not Jennifer and no one else would. But that's the concept we're using here. Okay, so what we're trying to model is... Sorry.
Claire would after the discussion at lunch.
Sorry, I wasn't going to pick on Claire.
We had an interesting discussion at lunch. Anyway.
Okay. So there's some models of price setting agent defining network systems. We assume non-valuation, that's everything's public knowledge. I'm using subgame perfect equilibrium, that is the price setters move first. What's interesting here that we don't require a centralized authority to impose a mechanism. Instead, price setting is a strategic outcome. That is a strategic game in which you set prices, yet we get the same kind of outcomes that mechanism design sets. I showed you one example, and I show you another example towards the end, where we get something very, very similar as what those kind of cooperative game theory predictions would tell, and yet we got it as a game theoretic, as a strategic behavior in a game theoretic setting without imposing it as a mechanism. What we try to ask is there a subgame, is there an equilibrium? I guess my concept is the subgame perfect equilibrium. How good is the outcome? That is, who gets the goods? Is the trade reasonable that happens here? And maybe I think most interestingly, certainly to me, that was my original interest, who ends up with the profit? So why did I want to know this most? I guess you should want to know the other two also. I want to know this most because I was interested in trying to understand how networks get formed, and if I actually put a network formation game on top of it or underneath it, I say, okay, and you can add edges, then we want to know in whose interest is to pay for edges, who's making money here. So this was my real question here. But I guess looking at it, one should resolve the other question, is how the goods move, is it reasonably good, and is there an equilibrium at all? And again, just a repeat of something I already said. My favorite example is the job market, which is nice because both parties distinguish each other, but all my slides will always have identical goods and indistinguishable goods and identical people, just because it's simpler to do those slides that way. So I guess result number one, subgame perfect equilibrium exists and exists in pure strategies. So it's kind of really simple. You can just offer prices. What do pure strategies look like? I guess it's a number attached to every edge. That's the offered price.
Even not everybody here is a game theory person, so could you just say what subgame perfect equilibrium is?
Yeah, I was planning to hide this, but okay, not a bad idea. So I guess looking back at this slide, life went in two steps. First, the middle people offer prices. This is what you see right now. Every middle person offered a price. For some weird reason, two prices I forgot to put on. Imagine there's some numbers sitting there. See those, I had to point. Those two things are missing. I apologize. That's a first step. The second step is that the sellers and buyers will react to those prices. Now, how do they react to the prices? It's reasonable to say that they're going to react to what my slide will show as soon as I try to move it. Namely, everyone takes the best offer. So if you're a seller, your best offer is the highest price. If you're a buyer, your best offer is the smallest price. And in this game, this particular instance, this will work out well. This guy took that highest price, and this guy took that highest price, and indeed the goods moved according to the red edges. Now, the assumption that the buyers and sellers take the best price, this is what subgame perfect means. That is, after the price is offered, everyone has to react locally optimally. In the ultimatum game, Jennifer reacting locally optimally to my generous offer of 1 penny is to accept. Strategically, in a non-other word, she can tell me ahead of time that, wait, Eva, at least you offer me $50 or else I won't accept. But if I use subgame perfect as an equilibrium notion, she can tell me all kinds of threats, and then I offer her a penny, and locally her best interest is to accept the penny. And this is what subgame perfect equilibrium is. So in this case, it really means that I'm assuming that the buyers and sellers are drones. They simply take the best offer. And the game is really happening in the middle. The interesting part of the game is the price offers. And so what it really means that on that game in the middle, there is a deterministic equilibrium. Does that make sense? Yeah.
Are you assuming that all the sellers here have only one thing to sell?
On the picture, yes. On the paper, not. Yes. In the picture, everyone has only one thing to sell.
And also, like the traders, we can
That would be a big problem. So I allow them to price discriminate. This is a reasonable assumption in a lot of the network setting. Some places it's not a reasonable assumption. So they allow to do what they're doing here is a trader here in the middle has 3 edges and they're setting different prices on the edges, and I allow them to do that. And if I insist that they have to offer the same price, that, for example, makes this go away. There's no equilibrium, not necessarily equilibrium. There are a lot of things that are modeled well with allowing price discrimination. And in particular, the physical network or who connects to whom, those are usually setups where one node in a network is like, so this is a low market here and this is another little market, either another village or it's a financial market and one of them is the New York market and one of them is some other market, and you can actually offer a different price. But our game certainly gets more complex, and in particular, we lose the fact that there is a pure strategy equilibrium if you insist on offering the same price. So that's actually an important question. And that I claim that the outcome is socially optimal. Now, what does it mean to be socially optimal? I guess what I mean by socially optimal, that the total valuation of all these goods, all the people who get the goods are maximized. That the same notion of social optimality that people use in auctions, where you want to say that the guy who gets the good is the one that gets the highest valuation. What's important to note here is that this notion of social optimality ignores prices. It says that money doesn't matter, because however much money, whatever the offered prices were, money changes hands, then one guy gets poorer, the other one gets richer. That doesn't affect social welfare. Money is the thing to make the economy work. That's not the way to evaluate the economy. The way you evaluate the economy is who had the goods and who has them now. And that is how we're evaluating, and I claim that in all, there is a pure strategy equilibrium, and all equilibria have the property that the right guys, the ones that value the maximum, get the money. I'm using a valuation system where the seller is allowed to have some value. So, for example, that guy here didn't sell because his valuation is too good. His offers were just not good enough. Yeah. Question?
No, you said get the money doesn't make this good.
Oh, sorry. I might have said wrong. So what matters for social outcome or social welfare is the valuation for the good for the guys who got it, and not the money that changes hands, because that just changed hands. It didn't affect the total economy outcome. Okay, so yeah, it assumes that we normalize on money. And I guess this I don't know how to get away from. In even the sense that I don't have a good model without this. Don't have a good model of life without normalizing on money.
Because that's a big issue for economy, for small players and big players, the utility,
For money. Yes, yes. It's a very interesting question. In this context of this work, I don't have anything very good to offer. But it's definitely a very good question. Oops. So before telling you about who gets the money, maybe I want to tell you a little bit of how this connecting back to something that may be easier. You see that, well, this is reasonable to believe. So what is social optimal here? It turns out that this is very closely connected to a regular matching problem, which is not too surprising. I can think of a value of a trade, and I guess my trade here would be that seller I gets connected, his good goes up to buyer J, and I can say that, well, the value of that trade is the value difference between the buyer and the seller. As you realize, this won't depend on this uniformity. It could be a specific value difference. If I match these two guys, what's the value of that? And I can think of this as the value of that particular edge, and what I'm looking for here is a way to match buyers and sellers that maximizes the value of the matching. So algorithmically, it's simply a maximum matching problem. The matching problem that tries to match up the buyers with the sellers to maximize this total value. I guess the graph I'm thinking of is an induced bipartite graph in which the buyer and the seller is connected. If there happens to be a trader that can induct that trade, for example, this buyer here and that seller over there is not connected because they simply can't trade. There is no trading route between them. So if I think about the second question of who ends up with the profit, then I guess here is again our auction example with the one trader getting the profit. But one thing that is sort of distressing, or one needs to realize this first, as an interesting example, that trader profits not actually set by the system. It might differ. So look at this particular simple example. Again, it's a funny mix between competition and monopoly. There's 3 monopoly edges. That is 3 edges on which the trader has complete monopoly. The other edges, it's a bit more complex, and it turns out that for any value of x and y, there's an equilibrium in which the prices are offered as I indicated. There's one edge that I'm currently missing on which you have to offer the maximum of x and y as an equilibrium value. The trade will occur on these straight edges, and which I should have indicated, and the total profit will be here that the middle trader makes, the trader on this line makes profit y, the trader on this line makes profit x, and the trader in this line makes 1 minus x, which is a total profit of, assuming x is the maximum, which is the total profit of somewhere between 1 and 2. It depends which equilibrium they choose. So unfortunately, the amount of money a trader can make depends on which equilibrium they choose. So I guess in offering any results on equilibria, I guess, and here comes the second connection to a trader T can make profit if and only if one of his connections to a seller or buyer is essentials for social welfare. So if you think about, I guess, the theory you wanted to offer, whether it's cooperative equilibrium, cooperative game theory, or you can think about it as a mechanism design problem, the traditional value a trader gets evaluated whether the trader himself has value to the society. If the trader goes home and no longer trades, then I guess social welfare decreased because this guy went home, maybe. And he should make an amount of money, maybe, that has to do with his value. Here I'm offering something a little bit weaker. Says that if he disregards one of his links, so he, for example, kills this link, then I guess he should make money if and only if he can disconnect one of his links, and that's essential, that decreases social welfare. So very analogous to this VCG payment, which would be his value to society, but not quite it. But at the same time, if you think about VCG is sort of the mechanism design version in which we can induce socially optimal outcome by offering people the right prices, this mechanism design problem usually suffers from not being able to balance the budget. In order to make all of us, all of you guys behave optimally, I have to offer separate payments to Jennifer and Anna and Claire and everyone else, and there's a little problem usually there. I have to offer more money than what I have. It's not balanced. I'm not making enough money to keep everyone happy enough. Here I keep it budget balanced. This is a strategic game. It's budget balanced. In fact, there's no mechanism designer who can or cannot offer money. And we get something similar, but not quite it, as to what the outcome is. It has to do with how essential he is. Possibly, yeah. Even that way is budget balanced. The traders will definitely get positive money. You can't get negative money. VCG usually ends up with a deficit. You had to pay out more than what you had.
The buyers and sellers together have lost something from this, whatever went to the trade.
Yes. Yeah. Well, yeah. But the sign is the opposite. In VCG, you have to offer them extra money. Here, they're losing something. So it's something different. But there is certainly an analogy.
VCG is usually not budget balance if you have long paths. And here, paths are only length 1. So is it also, are there examples of VCG that is not budget balance?
What am I guess.
Usually it happens when you have a long.
Yeah, yes, it's not budget balance here either, and I guess because my forwarder is not so great backwards, let me come back to your question in a minute, or in a few minutes, okay? I'm sorry. So let me try to tell you a little bit how what makes these proofs work. I won't do all the glory details, but I think I can give you in 2 slides enough of a hint of what sort of, how one goes about proving this to the level that becomes believable, I think, that, oh yeah, I guess something like this should work. So I want to first start with the optimality, and maybe that's the only thing that I really want to tell you. So what was optimality is the buyers and sellers, and we want to evaluate when you conduct a trade, we want to evaluate the difference in valuation. This was a maximum matching problem, which I already told you about. You can think of an edge as connecting a trader and seller, a buyer and seller if there's a trader that can help you connect the stuff. And the maximum value of a matching, you want the maximum value matching problem. And people, again, edge is connected via some trader. Value of an edge is the difference. And again, to make my life simple, I'm going to cheat here and think of this example, which I already had on the slide, called pair traders. This is an example, the trader sitting on every edge. I know in reality I want to think of traders that are more complex. In a minute I come back to that. But this is the only place where I really can tell you what the proof is. If every edge is a separate trader, which is certainly easier. Otherwise, these traders sometimes are the same identity and have conflicting interest, which I have to take into account. In this case of pair traders, of course, I'm going to want to think of it as a bipartite graph. And now I really can think of it as this way. Every edge is a separate trader. And I want to think of this value Vij, which I introduced earlier, is the value difference between seller I and buyer j. That is the value on trading on the edge. I want to think of this in a minute for about 2 minutes. I want to think of this as a linear program. This is a standard linear program for matchings. It says that there are these variables which I could call xij's. Xij is a variable you should think of as 0, 1. It says that if I sum overall sellers, the xij's of the different buyers, that should be at most 1. He has 1 good, and he can sell it to 1 seller. Similarly, backwards, if I sum overall the buyers, the seller has 1 good, so can only trade with 1 buyer. Less than or equal, because he can keep it or not trade. And this is the total valuation if xij turns out to be 0, 1. And what's nice on bipartite graph is that you solve this will turn out to be xij 0 and 1. What's interesting for us, and that's the one insight I will want to leave you with, that instead of this, I want to think about this as linear programming dual. If you remember maximum matchings, then that thing I wrote down there is a linear programming dual. It has numbers associated with the nodes, which usually called yi's and yj's. And the only rule about them is that the yi plus the yj offered on the 2 ends of an edge I and j should be bigger, sum to bigger than valuation. And what I really want to tell you, that this story tells you what on earth these v's are. So if you're one of the linear programming fans, you recognize this. If you're not one of the linear programming fans, you don't recognize this. But the only message I want to tell you about this, I know the names of these yi's in a way that you will definitely recognize or remember that, oh yeah, that's what the dual is. So what are these yi's? I claim that the yi's are the profits. This is how much money these guys make. That's what's called a yi. So let me try to convince you of this. So I claim that the seller and buyer profits, those are the linear programming dual variables in solving a linear program. So I wrote up a solution here where I indicated the profits people make. So remember, these guys don't necessarily make money. What I indicated as their profit is the difference between the valuation and the price. So if this guy had a valuation of 1 for the good, sold it for 3, he made a profit of 2. And over there, here's a guy whose valuation was 8, and he bought it for 8, so he made 0. Someone else might possibly have a situation in which he has a good, his valuation is 7, he buys it for 5, he would make 2. So I think of that as the valuation. If we can indicate that these are indeed the dual variables, and they satisfy some sort of optimality constraints with the primals, which then I guess they would automatically prove that this is socially optimal. And in fact, this is also our algorithm to show that they exist. The existence proof, namely, would say that simply solve the linear program, read off the duals, those are the profits, you're done. So this is where I want to make it believable rather than make you drive through the proofs. So why are these linear programming duals? What they really are is I have to go through this very simple duality constraint. So I have to say, okay, if someone's dual variable is non-negative, then linear programming tells me that some corresponding primal inequality has to be equal. That's a linear programming constraint. What does that mean in English? person I, maybe called a seller, made money. Well, I'm sure he sold. You can't make money if you don't sell. So of course it will sum to 1. No wonder. If he didn't sell, he couldn't have made money, right? Same story on the buyers. The buyers only can make money if they buy. Otherwise, nothing happened. So same inequality holds on that side. I cheated a little bit, and this isn't quite the linear program I'm really using, because our traders can make money too. In fact, this trader here where I indicated the red 5 made $5 on this trade. Oh, yeah, 8 minus 3. That's how much money made. That's, so I have to have a linear program that gives the traders variables too, which I should have changed my linear program to have. But his constraint says that if the trader makes money, then it must be the case that his variable is 1. No wonder. You can't make money if you're not involved in a trade. Or other way to put it. And then finally, it should say that if a trader doesn't make money, then there's some inequality about it. This will be the feasibility constraint. This is the one constraint I had on the slide, that yi plus yj should be less than or equal to value. Again, you're not too surprised. If I look at a trader that's not involved in a trade, say, for example, the trader up here, what does it mean that he's not involved in a trade? He's an independent trader. If he could be involved in a trade, he would. So it must be that his neighboring two edges are selling and buying so that there is no trade opportunity there. They're already eating up all the money. He's either left with negative profit if he tries to trade, or with 0 profit, something that's not worth trading for. That's the dual inequality. So what's nice here is that you're not supposed to think of the prices. Those are the wrong variables. It's the profits are the right variables. And the profits satisfy a very natural kind of rules. You can't make profit unless you trade. The profits should sum to the right thing, or else someone will trade it out from underneath you, which is the last inequality. So the linear programming offers you an explanation of what the linear programming dual variables really mean, and in fact also offers you a construction, solve the linear program, and it gets you prices. It also helps you, so I guess this was my first theorem, sellers and buyers' profits satisfy complementary to slackness, and hence trade must optimize welfare. Yeah.
So if you go back, these VIJs, those would be the difference?
Difference.
The buyer, the end, the
Yeah.
edge? Okay.
Yeah.
So this would be 7 to the 5 plus 2.
Yeah, exactly. And that secondary, if you solve the linear program, take the dual variables, those are profits, those imply some prices to make sure people got the right profit. That gives you an equilibrium. Extends also to general traders, which I didn't tell you why, but the extension is not actually technically so hard to do. And definitely extends to distinguishable goods. I never used that the Vij was Vi minus Vj. It could be any other number written that this pair induces to each other. That's the value of this pairing, independent whether it came from a difference or not. It also will give you a hint of how to prove the theorem about how people can make profit. It's a bit more complex, and I guess I won't go into the details there, because in order to have an interesting version of who can make profit, I have to think of more complex traders, not the pair traders, and I have to think of how this guy can make profit. I guess the theorem I claimed was the trader can make money if one of his connections to sellers and buyers are essential to social welfare. In order to think about this, okay, I guess I won't prove this. Instead, I'll give you one example, and maybe I'm using too much time. Is 1 more minute okay, or is? Yeah, I didn't realize how late it was. So there's one very interesting example that I want you to leave you with. I don't know what's up with this dumb machine. Well, we're going to start thinking about it on this slide before this wakes up. I don't know what's up with my machine. So this actually gives us an example of a situation in which trader is essential to the market and yet can't make money, and I want to leave you thinking whether this is a good model, a bad model, and what would be a better model. So here are two traders on this example. The interesting trader is trader T, connected to two buyers and two sellers. He is essential to the social welfare. So let's take him off and think about it. Without him, we only have access to one good, because he has two goods, the other guy has one good. The two buyers obviously can satisfy them both with one good. He's essential. Second, none of his single links is essential. If I take off any of these links, there's still two goods. And if I take off any of his connections upstairs, he's still okay. The other guy can help. He's essential, but none of his individual links is essential. So it's an interesting example that differentiates the traditional VCG from what I got as a theorem. I claim that in this theorem, this trader T cannot make profit, even though he's essential. Okay, unlike in VCG, in which he should make profit. Yeah. So let's try to at least convince you that indeed he cannot make money. So how would I convince you that he cannot make money? It's hard because my theorem is that no equilibrium doesn't make money. How am I showing you no equilibrium? So for talk purposes, I think this is my best convincing argument. He tries. He tries to make $1. He offers this set of prices, and this looks like it's pretty good. Both traders made $1 reasonable. But it's not an equilibrium. Because in the equilibrium notion, this trader would say, well, wait a minute. Why am I letting the other guy make money here? I guess I could undercut him. Offer on that blue link instead of $1.99, that would undercut the guy, and I get $1.99. So what I have on the picture is not an equilibrium. And in fact, you could imagine that there is no equilibrium here that has any numbers other than zeros on the upper links. These two guys compete each other out of business for some reason.
But what do you do about Yuval's question?
Yeah, I can't answer Yuval's question. In fact, I was going to point it out as my next point, that, of course, what he could do is cut his link. So I guess you can answer, so if he only didn't have the blue link, I guess I didn't expect Yuval's question to show up, and hence that slide will be 2 over. I'm sorry. But I can use this slide to at least talk about it. If he only cut this link, he would cut this link up here. That's the one to cut, or one of the upper links. Then all of a sudden he can make money. So there are 2 things you can think about. One, and I guess one is an explanation to say that people are not this smart. They do in a situation like this, it's so damn tempting to undercut the other guy that what really happens in market is people undercut and act with each other, and at the end make no money, even though they should be smarter. That would be a sportive of this model I'm using. I would love to use Yuval's model, and I would like to have a principled game theoretic definition of what does it mean to think ahead, to realize that if you only cut your edge, you're better off. I don't know quite what it means.
I mean, people like provide different, you can get like connection to the internet only with one provider and don't compete. Like,
Not necessarily for this, because okay, maybe. But if you want to think about the principled game theoretic version that says, okay, tell me what you're thinking, I actually cannot, and if Yuval or one of you can, or Yossi or whoever can, it would be really neat. I would love to say that he will think one step ahead. But it's hard to think one step ahead, because while I think one step ahead, how do I think one step ahead? Assume that you don't think one step ahead. If I make this symmetric, there is a circle here that I can actually close. And I both talk to game theorists and ask people, it's not clear what's the clear way to close this circle. That you actually, without cutting your link, if I don't allow, it's not a 2-step game. If it's a 2-step game, I guess I could do that. Because say step 1, you cut any link you want, and step 2, find an equilibrium. But if I want to have an equilibrium notion in which a 1-step game, I somehow would say that reasonable people would know to offer these as prices. Don't undercut each other. I don't have a principled notion of what that would mean.
That would be actually illegal by at least your 3 months.
No, actually. If we didn't agree to not undercut each other, it's not illegal. Outside agree, yes, no, because collusion is if you and I enter an agreement about this. If you do it without an agreement, it's not collusion.
Oh, fine. So that's
It's hard. True.
So it seems if you go back to that example, the real problem is your supply is in excess of demand.
Yes.
And you come up with situations all the time where, there's overproduction of goods that drives prices to zero. People don't make profits in the situation. So in some sense, if you're in a circumstance where you don't have this overproduction, can this, I guess you can locally by the,
I think the link doesn't change the supply or the demand.
Well, I'm focusing on cutting that link. Instead, I could cut this link.
I think none of those links is essential. So cutting one link makes the other link essential. Since you have differential pricing on both the links, in some sort these links are the traders and not the nodes. And really these two traders, none of them has any market power here.
Maybe. Yeah. Because I guess there's one trader around here. Okay, so on the plus side, what our results offer, and I guess I had it on the slide, but maybe didn't read it out, is joint work with Larry Blume, David Easley, and Jon Kleinberg, that we offer a strategic game, a game in which price setting is a strategic outcome. The equilibrium notion we use, I think, is the most natural one, the subgame perfect equilibrium. It certainly has some weaknesses, but it's a natural notion. Pure equilibrium exists. It's always socially optimal. Can characterize who makes profit, who can make profit and how much. I didn't put that on the slide, but equally the same sort of theorem can tell you maximum how much you can make or minimum how much you're going to make in every equilibrium. There are a couple other price setting games which I guess I put here two references for price setting in many other contexts. I really like Adrian Vetta's facility location game. Adrian liked to phrase it as a social society and a broader context, and it has many other applications other than facility location. But in this context, the most convincing application is facility location, in which you can think of it also as a subgame perfect equilibrium sort of concept. His version is that you locate and then the prices are a second stage. In fact, I have to think of Vetta's solution concept as a three-stage game. Locate, set the prices, and then the users react to this as a three-stage game. Just like in this game, you can think of the second and third stages there as sort of drones. You can drive what the solution will be. Vetta officially defines this in his paper without any discussion, but you can derive his concept out of the same subgame perfect equilibrium. What's nice there that it is actually a pricing game. And the prices, again, come out to be something natural. In a way, pricing is not the primary object there. It's the secondary object because it can be automatically derived out of the location. There is a link pricing with delays where I think the two people that contributed the most is Atsamoglu and Ozdaglar. They have a bunch of sequence of papers which actually tries to add pricing with delays, so combines the congestion game style of feature with a pricing feature. They're nice papers. Unfortunately, they only work on parallel links, so they had to lose the network structure in order to get anything. But there are many other contexts in which we should try to understand pricing, and maybe most dominantly, algorithmic game theory has a lot of many other issues that I'm only beginning to. I offered pricing as something as a focus for this talk, but there are many other issues that we should all think about. In particular, I want to think about, and I guess my two favorite things is cooperative game theory, that is, get away from Nash equilibrium as a solution concept and try to think about what cooperation here really means. Maybe two papers that I want to point to as starting to begin. There is an EC07 paper that about strong Nash equilibrium that assumes perfect cooperation. Every subgroup is trying to cooperate. And I have a paper with Ara Hairapetyan and Tom Wexler about a year ago where we trying to not do this. Perfect cooperation is nice, but probably hard to arrange. And it tends to end up with not having an equilibrium. But instead, we try to have a notion of partial cooperation. And I think anything in this space trying to understand cooperation would be important, and any mix between the Nash equilibrium-based analysis and a more cooperative game analysis would be very important. And the second thing I think I'm equally interested in, and I guess I'm more recently working with Bobby Kleinberg in some version of this, is equilibrium selection. So one important thing that came out here in the beginning, that who makes money depends on which equilibrium the users end up in. And it would be nice to have any prediction of which one they should end up in, which one they do end up in. As proud as I was on that we ended up with a game theory where price setting was strategic outcome, I do like the atonement process, because that's a natural process that somehow models what happens in prices. And what I really would like to do is a atonement-like process that selects equilibria, where you have best of both worlds. You have a natural atonement-like process, which hopefully, unlike a lot of what happens in the pricing games or market equilibrium games, converges and converges fast, and it selects the equilibrium for you. It tells you which equilibrium it wants to converge to. I guess I'm starting to work on this, and maybe this is a bit too high a goal to achieve in all games, but hopefully in a large number of games it will be possible. I think that would be more convincing than either just a atonement style process, or what I offered here is just a game theory equilibrium style process. You kind of want them both. If they match, you're really neat. If they don't match, we'll cross that bridge when we come to it. And thank you very much, and sorry I ran over in time.
How the price that you get relates to the price that you get from a BCG? Are they related in any way?
No. No. For sellers and buyers, the maximum possible value they can make is the VCG value. But as we know, they can't simultaneously make that much, because VCG is not budget balance. In order to offer VCG prices, I have to pour money into an economy. So you individually, there are many equilibria. The one in which you, Yossi, make as much money as possible, you make your VCG value. But unfortunately, in that case, Anna can't make her VCG value, because I insist on budget balance. And if you all make your VCG value, that drives us above the budget line. Okay, so where the VCG connection is in, the highest amount an individual can make is what he would make in VCG. You should not be too surprised that that's too high. You can't simultaneously make all this much, because VCG is not budget balanced in the other side, i.e. The total amount made is too much.
Even on budget.
Even on budget.